So, let us again indulge ourselves in the pleasures of linear programming. So, here is the problem that we are going to study, minimize C transpose x subject to A x equal to B, x greater than equal to 0. I will just list down everything where C is in Rn, n could be anything, it could be 2, 3, 4, 5, it does not matter. A is a m cross n matrix and the rank of A is m, B is of course element of Rm. X, the decision vector, naturally is in Rn, which I do not have to specify because you take a inner product. Now, if I want to solve this problem, it is very important to know what is the feasible set, that is, do I or can I find points of the following set. Now, how do I go about doing this? What is the easiest way of finding a point? Now, this thing can be done through a little trick. The trick is as follows, that because you know that rank of A is m, that is A is of full row rank, what we can do is the following. We know that thus A has m linearly independent columns. Of course, m is less than equal to n. This is quite a standard thing, because the maximum number of linearly independent vectors that you can have in n space Rn is n. So, thus m has m linearly independent columns. Now, suppose by a stroke of luck or by what we call multiplication with permutation matrices, I find that the first m columns that I have of the matrix A is actually linearly independent. So, it may not be so easy to determine which vectors are linearly independent if the matrix is very large. Then there is certain trick by which we can do something, but let us just assume for the time being that I can partition the matrix into B and N, where B is a m cross m matrix. So, B is a matrix whose rows as well as columns. So, these first m rows and these are n minus m rows, m columns. So, the first m columns of A are linearly independent, and taking those columns and the rows themselves, I form a matrix B. So, B is an m cross m matrix, and you know this I have partitioned the columns. So, this m cross m matrix B is invertible because it has m linearly independent rows and m linearly independent columns. So, B is invertible. Now, because I partition the matrix into B and N, any feasible vector can be partitioned into two parts, x b and x n. So, take any vector x, let us write it down as x b and x n. So, x b corresponds to the indices, is a vector corresponding to the indices or the indices of the first m rows, and the next one corresponding to the indices of the last n minus m rows. So, here I have m components and here I have n minus m components, and let us assume that x is in C. If x is in C, then I must have A of x is equal to B. If I have A of x equal to B, I can write down this as B n. So, this is a partition matrix, but you can think of this itself as a matrix with 2 components, and then you can go on doing whatever you want in the same policy, in the same way you do matrix multiplication. So, now what you have is B times x b, matrix B multiplied with the vector x b, and n times x n is B. So, x of B is B minus n x n. So, this would imply B of x b is B minus n of x n. So, x of B, using the invertibility of B, it is B inverse B minus B inverse n x n. So, what do I get from here? So, x n is free. So, if I can choose whatever x n I want, I can put any value to x n, then I can get x b, and hence I get the vector x. So, to compute a feasible x, we have x n free, and putting in any values to the components of x n, as I did desire whatever I want to the components of x n, I get the vector x b. This is clear to everyone. Now, if I choose x n is equal to 0. Now, you might ask me why I have written as x b and x n. We will very soon come to the point. Just for the time being, just take on these symbols, and I will come to the point very soon why x b and x n. If we choose x n equal to 0, we have x of b is equal to b inverse b, and then x, this vector is called b inverse b 0. Now, if b inverse b is greater than equal to 0, it implies that x is a member of the feasible set C, because it satisfies x equal to b and x greater than equal to 0. So, any feasible solution, so if x is element of C and x is written as b inverse b 0, then x is called a basic feasible solution. And that is why this x b x n equal to x, this is called the basic part and this is called the non-basic part. So, when non-basic components are all 0, the feasible solution that we get is called a basic feasible solution. So, this is a basic feasible solution. The most fundamental result in linear programming is that a basic feasible solution corresponds to an extreme point of the convex feasible polyhedra. So, if you take the polyhedral set, which is the feasible, the set C, then every extreme point of C is a basic feasible solution to the linear programming problem, and every basic feasible and every extreme point is a basic feasible solution, and every basic feasible solution is an extreme point. And in fact, it can be shown that any optimal solution is a basic feasible solution, and hence is attained at an extreme point, is itself also an extreme point. So, what we are doing in linear programming is computing the functional values over the extreme points and then trying to find which is minimum, but there could be huge number of extreme points if your problem data is large, that is there are a lot of decision variables, there could be millions and trillions of extreme points, a thing which you can't view, nobody can view, it is so difficult to think about it. Now, if that is the scenario, then you cannot geometrically view it, neither can you do enumeration of a huge number of points, the function value, it will simply slow down the whole process. So, the whole question is that if I know that I am at an extreme point which is a BFS, but it is not a solution to the original problem, we will show under what conditions you can check that it is not a solution to the original problem. Then what we can do is, by a clever way which is called the simplex method, is we can move from one vertex to another vertex, so that the functional value, the value of C transpose X actually goes down as I go to a new extreme point. So, I have to find a clever way to keep on moving from one extreme point to the other, but at the same time keep on decreasing the function value as I keep on moving over the extreme points. So, I do not cover all extreme points, only cover some few of them, but I reach the solution. So, it saves enormous amount of computing time, enormous amount of effort, enormous amount of mental stress and so much that this process, which is achieved by the simplex method in quite a simple way, is as a result very popular and is one of the most elegant algorithms in optimization theory. So, what is the idea? So, let us write down a theorem. We have not written down theorems for a long time. So, we write down a theorem. You need not give it a number, but mathematicians likes to state very state of the art important result, I would say, not state of the art is a misnomer. Very important fundamental results are usually given as theorems. So, now you might ask me, how do I know that there will be an extreme point of this convex set? Could there be a convex set which does not have an extreme point? Could there be a convex set which does not have an extreme point? I am asking you this question. Think of an example. Can you find a convex set which does not have an extreme point? Now, consider this feasible set. If X is an extreme point of C, actually there is a major result in convex geometry which says that every convex polyhedron set has an extreme point. If X is an extreme point, then X is a basic feasible solution whose shorthand throughout the world in any optimization book is always BFS, and BFS, and X is a BFS and vice versa. In other words, X is an extreme point if and only if A, the matrix A, can be decomposed into the partition B and N such that x equal to x b x n equal to B inverse B 0, where B is an invertible matrix. So, x, so if x is an extreme point, it can be represented like this, and if x can be represented like this, then x is an extreme point, where B is an invertible M cross M matrix satisfying B inverse B greater than equal to 0. So, this is what is called a BFS. So, anything or any thing, we will give some slightly more general versions of this, a very different way of defining things. So, what we have is this following result, which is very fundamental, found in any linear programming book. Now, given any point x in the set C, x can be represented as any vector which has some point 0, some point non-zero. You can always represent them. Maybe the number of non-zero variables, non-zero components are not there, all are positive. It could be like that, because there could be something internal, x must be strictly greater than 0. But in general, I can always write a point with some zeros, some non-zeros. So, let me just tell you how to go about proving this very important result. Now, let me do the proof. Suppose A can be decomposed. I want to show that if I have a BFS, it is actually an extreme point. A can be decomposed into Bn with x equal to this is whatever I have assumed in the result. Now, to show that x is an extreme point of C, now, x is of course, if I have this, x is of course feasible. So, step 1, let us show that x is feasible. So, let us show first, because I know just this decomposition, I know that x is greater than equal to 0, all the components are greater than equal to 0, but I do not know whether it satisfies A x equal to B, which is a major thing that we have to check. So, let us first show that x is in C. To show that, let me compute A of x, which is A, because by the hypothesis A is decomposed into two parts B and N, where B is an invertible matrix M cross N, and x B and x N, which is B inverse B and N, which is B N and B inverse B 0, which would give me B inverse B plus N into 0, So, that would be nothing but this would be identity, because this is invertible matrix, B into B inverse P is identity. So, it is B. So, what I get is A x equal to B, showing that x is belonging to C. So, to first show that x is an extreme point, my first step is to show that x is in C and then show that x is an extreme point of C. Now, the next step, we will do our proof by the method of contradiction or reductio ad absurdum, as known to Greeks. But many mathematicians would not really like proofs by contradiction. They would rather like straightforward proofs, straightforward or maybe even constructive proofs. But in certain cases, it is much more easier to prove by contradiction. That is, whatever we want to prove, we take an hypothesis completely opposite to that, the negation of that, and then we reach a contradiction. That is, some actually given hypothesis is contradicted because we have assumed that our original claim is wrong. So, it means if our original claim is not correct, then there is a contradiction in our actual hypothesis, which means if our actual hypothesis is true, it implies that our original claim is also true. So, it is P implies Q, negation of Q implies negation of P. So, this logical structure is used in the proof by contradiction. So, let us do the same thing. So, we will prove by contradiction. So, let x be not an extreme point. Not a good English here, anyway, does not matter. If you understand what I am trying to say, it is fine. Okay. Now what? Now, which means that there must be two distinct points in A C. So, when I take a convex combination of them with lambda between 0 and 1, then x is one of those points. So, there exists x 1 not equal to x 2, x 1 x 2 in C, and lambda in 0 1 such that okay. So, x is represented as B inverse B 0. So, B inverse B consists of few vectors, few rows and columns. So, I am writing corresponding to the x b part, I am dividing x 1 into x 1 1 and x 1 2, and I am breaking up x 2 into x 2 1 x 2 2. You could as well as write x 1 b, x 1 n, x 2 b, x 2 n, does not matter. What I would have is that this has the same number of components as x b, this has the same number of components as x n, this has the same number of components as x b, and this has the same number of components as x n. Now, what would immediately happen is that I will equate with these vectors components here, I will equate the components of these two vectors. Now, because this part in the non basic part everything is 0. So, here just by convex combination, because x 1 2 is greater than equal to 0, x 2 2 is also greater than equal to 0, it would imply, which I will leave as homework for the details. Now, let us see what does it mean. It means the following. So, some part is 0. Now, I have A of, because x 1 is feasible, I have A of x1 is equal to B, which would imply again by the partition B x11 plus N x12 is equal to B, but x12 is 0 from here, from the above line, and this would imply x11 is equal to B inverse B. The same goes for x2, because that being an element of C and because it is already greater than equal to 0, it also has to satisfy, it is greater than equal to 0 and also has to satisfy x2 is equal to B. So, this would imply B x21 plus N x22 is equal to B, where again from the previous line we have x22 equal to 0, implying that x21 is equal to B inverse B. So, that would simply imply that x is equal to x1 is equal to x2. So, it contradicts that x1 contradicts that. And hence, it is an extreme point. So, this implies that x is an extreme point. The other part, the reverse, is slightly tricky. Now, for the reverse. Suppose x is an extreme point. So, x is not an interior point, which, so this implies that x is in the boundary of C. So, in general, so without loss of generality, basically in general we can write x is equal to so the first k components are non-zero, where x is an element of C, it is an extreme point. N minus k components. So, it could be that n minus k is 0, that is n is equal to k, but in general you can always write a extreme point in this way. Now, corresponding to these k rows, there are columns, k columns in the matrix A. So, we are going to show that the first k rows, suppose these are 0 k components, x I strictly greater than 0, I equal to 1 to k. So, these are non-zero components and these are 0 components. So, the first step is to show that the first k rows A1 AK, the first k rows of A are linearly independent. Okay. Again we will go by the method of contradiction. Suppose not. Then it must be linearly dependent. So, this set of vectors must be linearly dependent. Thus, there exist scalars which are real number because we are in a real field, lambda 1, lambda 2, lambda k, not all 0 such that lambda 1 a 1 lambda 2, this linear combination is actually 0. Now, construct the vector, construct a lambda in R n such that lambda is lambda 1 lambda k 0, 2 dots and 0. So, k components n minus k components. Now, I will construct from the given vector x 2 more vectors x 1 x 2. So, I will take an alpha now. As a homework, you show that we can choose alpha greater than 0 in such a way that x 1 is greater than equal to 0, x 2 is greater than equal to 0. Spend some time with this. It is a good exercise. Now, let us see what is a x 1. X 1, okay, I have got it to be greater than equal to 0 is a x plus alpha a lambda. Okay. Now, this is giving me a x plus alpha times summation lambda j a j at j is equal to 1 to m, because beyond m sorry, this is not k n, I made a mistake, it is m, this is m in R m, because this corresponds to m components, m columns which are least. So, maximum number of linearly independent columns is m. So, if k is bigger than m, we have to do something. If k is smaller than m, then fine, we already have it. So, if k is bigger than m, I can always reduce that number, I can always bring down and show that if once k is bigger than m, you cannot have they cannot be linearly independent, and that is the whole idea of doing so. Now, this is 0 because first k component is non-zero, which gives you the linear independent thing, the other part is 0. So, this is nothing but because other lambda is a 0. So, this is b. Similarly, a x 2 is b. So, which you prove yourself. Now, once I know this fact, observe that I can write x, observe, write x as half x 1 plus half x 2, where x 1 is not equal to x 2. So, if a 1, a 2, a k are, so if a 1, a 2, a k are linearly independent, linearly dependent, that is what, then x is not an extreme point. So, what I want to show is that if my a 1, a 2, a k are now linearly independent, I should know that because I have a has full rank m, I still have, and if k is, of course, k has to be strictly less than m. If k is not equal to m, if k is strictly less than m, then I can choose m minus k vectors from the remaining n minus k vectors and just join them up with this k a1 a2 ak and form a linearly independent set of columns. Now, as rank of A, do not mind, I can write rank as full or big letter or small letter, is m from the set of remaining n minus k column vectors we can choose m minus k column vectors which can be clubbed with a1 a2 ak to form a linearly independent set, because there are linearly independent columns. Let a1 ak plus 1 to am are these vectors. For simplicity, here or you just have to make a multiplication with the permutation matrix. So, ak1 plus dot 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 am are those vectors. Then one can write A is equal to b n with B formed of the first m columns is full rank, full row and column rank, full rank. And now, because x is in C, we have A x equal to b, implying b n. So, our x is x1, x2, xk. So, B inverse B is x1, x2, xk, assuming that k is strictly less than or equal to m 0, 0. So, here I have k row and here I have m minus k rows. So, since x j greater than equal to 0 when j is equal to 1 to k, this implies that B inverse B is greater than equal to 0, and that is exactly what we wanted. If x is a extreme point, then I can represent A in this form B and n, where B has all its rows and all its columns linearly independent, and x can be represented as B inverse B. So, anyway n the remaining part n into x n is anyway 0. So, and that B inverse B has to be greater than equal to 0, and that is our result. Now, that a polyhedral set as an extreme point is something we are not going to prove, because that it will take us off what we want to do, but it is not a very difficult one, and we can possibly do that. And the whole idea of BFS might come into play there again, but the whole idea of this proof will come into there again, but that is not a very big issue. The proof idea of this extreme point business, whether the polyhedral set as an extreme point, comes from the idea of proof of the Carat-Theodori theorem. So, we will not get into this business, but I will just ask you to think that for a polyhedral set the extreme points are always finite. Just think about it, why. Today we end our talk with this proof, which has taken quite a good amount of time, and we want to say that in the next class tomorrow we are going to prove a very fundamental result. This is something you have to remember. This is one of the most important results in optimization theory, in convex optimization, that if I know that a linear function has a lower bound, that which means that the dual problem is feasible. Once you know that the dual problem is feasible, you know that the linear program has a lower bound, and once it has a lower bound, there exists a minimizer for this problem. So, there is an extreme point where the solution will be attained, where the minimum would be attained. So, this is exactly what we are going to prove in the next class. Thank you very much, and I hope you have followed this proof and you have enjoyed this fascinating fact that every extreme point corresponds to some special type of feasible point of C, and actually the optimal point, if the optima exist, it is in one of these basic feasible solutions, and that is exactly what we are going to show tomorrow, and we will prove this very important fact. And since you have already learnt about duality, and you know from weak duality that it is very easy if I have to just construct the dual problem and check its feasibility, and we will tell you how to check feasibility of a system of linear equations very soon, and that can be done by one of the type of simplex methods. And we will tell you that once you know that there is a lower bound, it is immediately clear that there is a minimizer. This is a very important fact from the point of view of computation, because nowadays there are many standard algorithms which once you give in the input of the primal, they know the inputs of the dual, because the dual inputs, dual data is generated out of the primal data, there is no extra data anywhere. So, in optimization, beware if you are studying duality, if you see any dual problem which has some data which does not seem to appear in the primal and suddenly come into the dual, then beware of such duals. Any dual problem has to be created out of the data of the primal, because that is the only data you have. Any other problem that you want to say is running side by side with the same problem has to be generated with the data of the original problem, and that is something you have to keep in mind. So, thank you, good night and goodbye.